Good afternoon. Welcome to the next session of Computational Fabrication Seminar. My name is Michal Pivovarczyk, and I will be hosting a session on core appearance reproduction. Today with me are two guests, a motivational speaker, Philipp Urban, and a deep dive speaker, Tobias Rittig. And I would like to first introduce our motivational speaker, Philipp, which received his master's at University of Hamburg and later his PhD at Hamburg University of Technology. From 2006 to 2008, he was visiting scientist at Munsell Core Science Laboratory in the Center of Imaging Science at Rochester Institute of Technology in USA. After which he headed to core research group at the Institute of Painting Science and Technology at Technische Universität Darmstadt in Germany. Since 2013, Urban has been the head of the Computer Center 3D Printing Technology at Fraunhofer Institute for Computer Graphics Research at IDG in Darmstadt and works with his team on the graphical 3D printer driver Cuttlefish. He is an adjunct professor to the Norwegian Core and Visual Computing Laboratory in the Norwegian University of Science and Technology in Norway. His research interests include 3D printing, spectral imaging, image quality, and material appearance reproduction. And please, the floor is yours.
Thanks, Michael. I will just share my screen. Okay, so welcome to my talk about the future of appearance 3D printing. I want to start with a definition of what is appearance 3D printing. So we have a shape and a visual appearance annotated to the shape. And we want to print this, like both quantities, like shape and the visual appearance. And for this, of course, we need a printer, but we also need a software. It's called 3D printer driver. And the 3D printer driver defines where materials are placed by the printer and also print process parameters. This information is then sent to the printer, and the printer should reproduce both the shape and the visual appearance. And yeah, what is visual appearance? We have multiple appearance attributes. One is color, which has 5 dimensions. Typically 3 are only reproduced. Gloss, according to Hunter, it has 5 dimensions, but usually only 1 dimension is reproduced, specular gloss. Translucency, which has at least 4 dimensions. And there are also other effects like chromochromatism, where the viewing geometry or where the color depends on the viewing geometry. And of course, you can also define this just by material appearance, by material properties like BRDFs or spectral data, BSS-RDFs. And in 3D printing, typically this information is stored in a texture, and the texture is mapped to the shape. Okay, let's have a quick look into the history of appearance 3D printing. The first full color printers came out in 2000 with binder jetting systems, and then we have the sheet lamination systems. And recently, like 6 years ago, full color material jetting printers came out from Stratasys, and like 3 years ago, approximately, full color multi-jet fusion printers. And the last 2 technologies are very interesting because the multi-jet fusion printers, they can create prints with a very high mechanical durability. Unfortunately, the appearance gamut, so the set of appearance quantities that they can reproduce, is very limited. So in contrast, material jetting is able to print a big variety of different appearance attributes, from color, translucency, gloss effects, and even haptic appearance properties like soft and hard can be reproduced. It has a very high geometric, can create high geometric details and high texture resolution. The only problem is that the mechanical durability is very low. And since all of the print that I will show you in the next slides are printed with material jetting, and I think Tobias will also show his approach for material jetting, mostly focusing on material jetting. I will give you a quick overview about the technology.
Once the material is loaded in the 3D printer and digital instructions are programmed, production begins as the jetting head rapidly moves along the x-axis, the y-axis, and the z-axis. Small droplets are sprayed by photopolymer jets in layers that are instantly cured by an ultraviolet lamp. Voxels, or three-dimensional pixels, are strategically placed during the build to allow for the combination of both flexible and rigid materials. The fine layers of digital materials accumulate on the build platform to create accurate final parts.
Okay, so that's a very quick description of the technology. And yeah, where you can find applications. So there is the traditional application is prototyping, but recently also the technology is found quite useful for surgery planning, where the data comes from CT or MRI sources, and the color is annotated, for example, to show tumors. Then, of course, cultural heritage is a big field where the technology is used to reproduce sculptures and artwork. Figure printing is actually a big business with millions of prints, movie making. And we were involved in the last couple of years in one application area, which is quite interesting, prosthetic eyes. So we have developed a system that takes optical coherence tomography data and pictures of the healthy eye to create a prosthetic for people with eye loss. Yeah, the first patient has been equipped with or supplied with an eye end of last year, and at the moment there are clinical studies going on. But if you look in all these application areas, you will see that there is no application where you have really functional parts that can withstand some mechanical force. And this is the problem of polyjetting or material jetting, the mechanical durability. And I can tell you, and this is something that I will also mention in the future part of my talk, that in future this will change, and this will open a lot of different application areas. Okay, let's have a look into an industrial digital workflow for appearance printing. And industrial does not mean that everything is already explored and it's basically a commodity, but these single building blocks, these single components of the workflow, there is still a lot of research going on and a lot of room for improvement. So we start typically with a pre-processing step where the object is placed into the build space. There's a texture sampling adapted to the size of the object, in order, for example, using mid mapping in order to minimize moire artifacts. The object is oriented in build space to minimize printing time. And then also texture is enhanced in order to compensate for light transport blurring. So you can see this here. There are also other approaches that work on the scattering compensation that don't use an industrial workflow, but this is also possible in an industrial workflow. Then the shape has to be decomposed in voxels in print resolution. And in graphical and appearance 3D printing, many models are not really made for 3D printing because they're, for example, scans or objects that are made for animation. So they are not watertight, they may have other problems. And so the robust voxelization is a big problem in appearance 3D printing. And there are a couple of solutions, for example, from Jacobson or Barrel using generalized binding numbers, or recently from Brandon using displaced sign distance fields approach. And then the next step is, since most of the prints or most of the objects are defined by a texture attached to the shape, the information of the appearance is just given on the surface, right? So this is a cut plane, and here you see this just on the surface is the appearance information. And due to light transport effects, you need to place also materials inside of the object because they influence the total appearance of the object. But in this area here, and this volume, there's now no information about the appearance. So you need to push this appearance into the object. And this is done by a distance field that basically defines or computes for each voxel within the volume, the shortest distance to the surface. And based on this shortest distance, appearance information is then pushed into the object. And then the appearance is in the object, or the appearance information is in the object, and we need to compute material ratios from appearance attributes. And this is in industrial workflows typically done by lookup tables. And this sounds a little bit like, okay, it's not really a complex topic, but actually to compute the lookup tables is a research field by its own, because it includes, for example, appearance gamut mapping. If you cannot reproduce an appearance, what kind of appearance you have to select from the reproducible appearance quantities instead to minimize the perceptual error, for example. So there's a lot of work still going on in this area. And finally, you have now the material ratios per voxel, and most printers can only fill a voxel with only one material. Some of them can also jet small droplets into one voxel, so you can have multiple materials per voxel, but in any way, you have a quantization of the printing system, and you have to account for this. And this is done by half-toning, and the ideal half-toning is a blue noise half-toning, because it pushes the quantization errors into high spatial frequencies, and the human visual system is less sensitive to these frequencies. So you can create a very, only with a few materials, you can create a lot of shades of color, for example. There is, of course, another interesting property of the printing system, because due to the light transport, you have a low pass filter, which means that if you have a blue noise half-tone, you will not notice voxels and the single materials even under a microscope. And this industrial pipeline works well, but it has one important limitation. The appearance is not really tuned to the object's geometry. So because you use lookup tables, it doesn't matter where you are in the geometry, you always transfer the same material ratio. And this is a nice reference and a nice motivation. It is, I think, my responsibility for the motivation talk to reference to Tobias' deep dive talk, because he presents an alternative approach using light transport. Okay, once everything is computed, the driver sends data to the printer, and this data looks like this. These are basically single slices with material positioning. And even for medium-sized models, in this case, it's a little bit larger, but not too big, you have already to deal with a lot of data, so 100 billion boxes in this case. And if you print this, you can see the capabilities of polyjetting or from material jetting. You see very, very small details that cannot be realized with any other printing system or printing technology. Good. What comes next? What is the future of appearance 3D printing? And this is something which is not directly linked to computational fabrication, but it's very important because it marks, I think, a tipping point. Recently, new printheads were developed. And these printheads allow printing very high viscous inks and also particle loaded inks. So it's like an order of magnitude higher viscosity that you can jet with these printheads. And this allows you to print mechanical durable material jetting prints. And basically there's a paradigm shift for the usage of material jetting from pure prototyping with a few functional applications, but only a very few, to really functional parts. At the moment, you can already, using these printheads, print dental certified SLA materials. SLA stands for sterile lithography materials for permanent dental restorations. So like crowns, bridges, and dentures. What is missing still is the appearance matching. This is something that we, for example, are now working on. The second thing that we will see in future is that not only color or translucency or gloss are reproduced, but a combination of all these quantities, all these appearance attributes. So today you can already create these effects. So you can create a really complex print. So this is not a random, this is really a print that shows you different gloss levels, of course, spatially varying color, different translucency, transparency levels. So you can create this. Sometimes post-processing is necessary, like polishing, but it is not that you can take an input and reproduce color, gloss, translucency, or even goniochromatism at every single point on the surface. This is at the moment not possible. Color matching is quite good already within the limits of the printer, but in the future, the idea is to measure and match appearance in printing. And I will give you some example how this could look like of our recent work on color and translucency. So we have developed a system where you can measure real materials, the color and translucency of real materials, and you can use this information to reproduce it in 3D printing. So that not only the color is reproduced correctly, but also the translucency. And for this, a normal industrial 3D printing, appearance 3D printing workflow is used. The whole idea is the appearance space behind this. So we are copying just 4 appearance quantities. These can be stored in RGBA encoding schemes, where the RGB is sRGB, the standard RGB color space linked to perception. And the A is the translucency parameter. And for this, we have defined, for this one-dimensional parameter, a new definition was developed by us. It's based on light transport measurements that induce image cues that are used by the human visual system to perceive translucency. So, for example, if we have lateral light transport, light goes into the object, is scattered, and goes again back to the observer, but at a different position on the surface. Then texture is blurred. You have fine geometric details are blurred, and these image cues are observed by the observer, by the human. And they judge not based on inverse optics. So the brain is not doing any inverse optics to compute absorption and scattering coefficients. It relies just on these very simple cues. And of course, if you see occluded objects, then you're in an optical thin area. And so we just use lateral light transport and vertical light transport to define this one-dimensional parameter. And reproducing this RGBA information reproduces also this light transport properties intrinsically because the printer is calibrated and characterized based on these RGBAs. And then you can create quite interesting things. For example, translucency, perceived translucency of an object is highly dependent on the size of the object. So if you see here these 2 objects, A and B, they are made by exactly the same material mixture. But this small object looks much more transparent or translucent than the big object. And this is clear because since the material is the same, the mean free paths of the photons are the same. But this object is smaller, so more photons go basically through the object. So this looks more transparent or translucent. And you can, of course, tune the absorption scattering coefficients to create of a small object the same appearance as a big object. And the interesting thing is that you can use just need to adjust the A parameter in order to get a much better match between the translucencies of these two objects. Okay, and the last thing that I believe we will see is a viewing condition invariant appearance matching. And this is, of course, very crucial for printing replacement parts that must fit into a visual environment, for example, teeth. At the moment, everything is adapted. So we have everything is adjusted in appearance 3D printing to only one viewing conditions, to one viewing condition. And for this viewing condition, you can achieve at the moment a very good color match within the limits of the printing system. But for the other quantities, it is already now a little bit problematic. But I believe this will be solved in future to some extent. But if you change the viewing conditions, even for today's prints, the input and the 3D print will probably deviate. And in order to make it invariant, you need to reproduce the physical material properties. And this is usually impossible. So the printing systems are are just too limited. And what is possible is to tune or select printing materials to a problem. So for example, you can select from a very big set of materials that are physically most equal to, for example, teeth materials. Or what is also possible, you can optimize the print for a few selected viewing conditions. So how does it work? So this is a work that I did for 2D printing some time ago. You can tune the viewing conditions or the print to one viewing condition that is most important for the application, and then use the remaining degrees of freedom of material selection to tune it for the second most important one, and so on until there's no degrees of freedom anymore for this tuning. And if you're interested, just look into this publication. Okay, so that's it. I have shown the industrial appearance 3D printing workflow, and there are three main building blocks of this workflow. One is the appearance is transferred, or the appearance attributes are transferred from the surface to the volume using distance fields. All these printing workflows use lookup table transformations from the appearance attributes to material ratios, and blue noise, half toning, 3D half toning is the choice to do. But they are limited because the appearance is not tuned to the object geometry, and this is a good motivation for Tobias. And what I believe will be seen in the future, we see a paradigm shift in material jetting from prototyping to functional parts. There will be more joint appearance reproduction of joint attributes. And the last one is a very open field still, viewing condition invariant appearance reproduction. And that's it. Thank you very much.
Thank you very much for the inspiring talk. And I would like to remind to the audience that they can post a question into the YouTube chat, and then we will ask them at the end in a joint Q&A session with both Philipp and Tobias. And now I would like to introduce Tobias, but I got a request to introduce him only very briefly, that he is a Tobias, and he is a PhD student in Charles University in Prague, and he will take over the introduction from now on. The floor is yours.
Yes. So thank you, Michal. So I will be connecting to Philipp's talk, and will be telling you how we can optimize the appearance using light transport simulation. So I want to introduce myself a bit. I'm from Germany, and this is where I did my bachelor's and master's at the University of Tübingen. And after a short stay in the industry in Munich, I went on to my PhD in Prague. And from there on, I did some internships at MPI in Saarbrücken, and I also visited where I met Michal actually, and I also visited Michal's current lab in Vienna. And yeah, so my background is in photorealistic rendering, the kind of rendering that you see in your car advertisements and movie visual effects. And so it came very naturally to me to apply this knowledge to 3D printing. So I structured my talk into 3 categories roughly. First of all, I will tell you more about the academic landscape, all the publications that have been published in this field. Then I will tell you exactly why this problem is so hard and why there's so much research going on. And later on, I will dive into 3 of my papers and show you roughly how we solve these problems there. So in my eyes, appearance 3D printing started roughly 2010, and it got off to a very good start where at the same SIGGRAPH 2 publications appeared that did the same thing. Fortunately, both were accepted and nobody had to go home, sadly. So before 2010, there were other works in appearance reproduction, but they used like machines like CNC mills or 2D printers. And here I want to focus on the 3D printing part. And these 2 works, they tried to replicate a subsurface scattering function that was virtually defined using a 3D printer. So they wanted to match a BSS-RDF and replicate it physically. Then in 2015, Philipp's group started essentially the color 3D printing in academia, as far as I can see. And that is with came with the technology, of course. Technology became available, and in this paper, which he roughly introduced in his talk, they showed how to go from the surface texture of in RGB color space to the printer materials that what the printer can understand. And so this is the goal of most of these early works. Similarly, Babai et al. Also tried to reproduce colors in a certain way using the printer's materials. And the difference between these 2 methods is that the newer method, Babai et al., tried to stack materials on top of each other, whereas Brunton et al. Placed the discrete materials next to each other, and both have their advantages and disadvantages. So I would put these into the color 3D printing category, the early works of that. Then 2017, Elek et al. Also proposed a method on how to distribute the colors in a certain way inside the volume, but they already went a step further and tried to compensate for some of the problems that are visible on the printouts at that time. And this was namely the lateral scattering effects that led to texture blur and reduction of contrast. In 2018, we've seen a paper of Shi et al., which uses a large set of materials and chooses from these to match paintings as accurately as possible. And they even went further and tried to match them in a spectral way. So really to get as close as possible color reproduction on these paintings. And they also used already a neural network for that. So they were ahead of the curve, which you will know soon. Then we just heard from Philipp about the works of Brunton et al. In 2018. It is sort of a paired paper with the Urban et al. 2019 paper. And they both look at the translucency or control of translucency or transparency in some cases, whereas the earlier paper is more about the technicalities and how to distribute the materials, whereas the second paper is more about the perceptual aspects and how to define this alpha parameter, as we just heard from Philipp. At that same year, we published a paper that took the scattering compensation approach from Elek et al. 2 years prior and applied it to 3D objects, and solved some solutions around thin geometry problems that you only have in 3D geometry, not in 2.5D planar slabs. Then our host today, Michal, published a paper in 2020 about gloss reproduction and how to bring this appearance phenomena into the 3D printing world. And yeah, recently, just like last year, 2021, we saw 2 methods with using machine learning again, both doing a sort of similar thing, being that they both try to predict what the color will be given a certain ink distribution in the volume. The difference between the 2 methods is that the Chen et al. Paper bases the results on real measurements, so they really printed out different colors and measured these, whereas in our paper we tried to match the network to a simulation and try to make it a more general rendering network to predict the appearance, more like a simulator. So yeah, so this is a machine learning characterization of the 3D printer. And in last year as well, we published with colleagues a completely new approach to this scattering compensation approach using differentiable rendering, and how to reformulate the problem in this space. And finally, also last year, 2021, we seen a paper of Brunton et al., where they incorporate again a new aspect of appearance, that is mesoscale textures, and that, I mean with that, haptic textures as well, onto existing objects. So here we see this football texture that is applied to a sphere, and how to make this working in a 3D printer. So essentially displacement maps, yes. So now I want to talk a bit about why is 3D printing, and especially color 3D printing, so hard. You've seen quite a lot of research been going on, and it's still not solved. So why is that? And for that, I'll show you a slab of material here. This is like just a big chunk of material, and that I'm illuminating with my phone LED. And as you can see, is that the light is scattering all the way through the object and is almost reaching the top surface, even though this is quite a thick chunk of material. And that means that the materials are very translucent. They're like far from opaque, in fact. And to visualize that even further, I put some numbers to it. Here you see that the light scattering, I would guess, is on the order of tens of millimeters, as you see in this picture as well. And this stands in contrast to the level of control that we have with modern 3D printers, where we have voxel sizes of in the order of tens of microns. So we have about 3 orders of magnitude difference between how finely we can control things, but then how coarsely these things react to us. So this is quite a difference in magnitude there. Now, like smart people would say, okay, why don't you just make the materials more opaque? Well, that's not entirely possible, because well, it is maybe technically possible, but for the 3D printing to work, we actually need this translucency. And first of all, we need a certain translucency in the UV wavelengths for the curing to be happening. And as you've seen in Philipp's talk, the 3D printer illuminates UV light to harden the material. So the UV light needs to pass through at least a few layers of material to be able to glue them together and to start the photoactivation process. And second of all, color 3D printing also relies on a subtractive color mixing system, which means that you're not adding red, green, and blue together to get your colors, but you're subtracting red, green, and blue from each other to achieve a certain color mixture. So just like in a 2D printer, you're relying on this CMYK color space. And there, the translucency is really necessary because you want to achieve finer color mixtures between these between these four primaries. And like if the light goes through more volume of different materials, then you can achieve finer details between these colors. So you get a higher color resolution. And there was a second point. Okay, so let's look at how the translucency actually affects our 3D printing. So say we want to print this Earth sphere there, and I'm showing you here on the right side what a default software of a 3D printer comes up with. And this is looking on the first glance really nice. We see blue, we see green, we see the mountains there with some gray. And now if you start to look closer, you will notice subtle artifacts. And this is, in fact, here, when you look at this cloud, it should be pretty white, but in fact, it's more like light blue. And that is because the dark blue of the water around it blurs into the light parts. And you will have this on any dark and light edges. You will always see some dark parts pushing into the light parts. And second of all, here in the center, in the desert there, we would like to see these very, very different shades of brown, but all we see is like one kind of washed out color. And not much of the texture sharpness is actually retained. So it almost looks like there's a blur kernel going on top of it. And this is the truth. As I told you, there's this like huge blur kernel that washes everything out on top of what we print. The problems go even further if we start to look at very thin geometry. I give you that. This is a very exaggerated example where like a 0.5 millimeter thickness, nobody prints that. But in fact, you will see such thin edges on any kind of 3D print because you will always have certain 90-degree corners, or you will have some small thinner parts so this problem still persists. And here we want to print these thin objects with 2 different textures on each side. And if we look on the left here, you see the painting that we try to reproduce here is pretty washed out. It's pretty light. There's not a lot of contrast going on between the blue in the back wall and the chair next to it, for example. And the problems get even worse if we look on the right side here, where we would like to have this nice cloudy sky of the painting, but all we can see is like in fact the window and the painting on the opposing side, like shining through the object. And this is again an example of a dark part spilling into the light part. So the dark window on the other side blurs over and talks to the light texture on the front side, on the back side. So why is this happening? Here I show you the 5 materials that we usually print with. And so this cyan, magenta, yellow, black is what you also have in a 2D printing setting, but in 3D printing, we also need to print our own substrate. So there's a white material. And if we look at the colored materials here, they are essentially subtractive color filters. So if we look at the white patch there in the cyan material, then what happens there is that the light goes through, red light gets absorbed, it hits the white background, gets reflected, and again red light gets absorbed, and we observe the front color as being cyan, which is the blue and the green still coming through, whereas the red is being absorbed. And similar effects, but other wavelengths are getting absorbed from magenta and yellow. And these are then 3 corners of your color space. And here on the right side, on the white material, we see some other effects going on. For example, on top of the black patch, it doesn't appear very black. In fact, we see it pretty bright. And that is because the light goes in and gets already scattered and reflected before it even hits this black background. And this is why the black patch looks much brighter than it should be. And the same scattering also is the culprit of this blurring that we see between the black and white edge. It doesn't appear very sharp, but we see this blurring going on. And here also in the black material, we see another problem, that the black is not very opaque. Again, it's very translucent, and the white patch is actually shining through this black material, although we would expect it to be, I guess, pretty opaque and black absorbing. So the gist is that these are volumetric optical properties, both scattering and absorption. And we need to handle them somehow, because they are always in any 3D printout, and we need to get control over them. So in the following, I want to talk to you about how we can compensate for these volumetric scattering effects, and how we can use light transport simulations to get this under control. So I want to tell you that there's sort of 2 different schools in the color 3D printing world, one being the top-down approach, and the other side is the bottom-up approach. They are different in that the top-down approach is more phenomenologically motivated. So they fit models to observations of real printouts and try to explain the observations using models. And the bottom-up approach is going a different route. It tries to explain the observations by modeling everything from first principles. So it tries to model it in a bottom-up way. And these 2 approaches essentially have different origins. That's why they developed both from the 2D printing world and in the computer graphics world. And you're very lucky today that you have speakers of both of these sides. Philipp is representing the left side here, and I will be now in the following talking more about the right side. And I hope we can have a very interesting discussion later on. So how do these 2 approaches differ technically? So in recent years, they've been growing quite a lot together, but like a fundamental difference is that we've seen this pipeline before in Philipp's talk, and here I only show it very simplified, so that what we feed to the 3D printer is actually, so we take the model, we voxelize it, we convert it to what the printer can understand in a way. These are all boxes that have very different implementations, and there's many to them. And last but not, and at last we can then 3D print these objects. And now this is the traditional pipeline that has been, I would say, inspired by a 2D printing approach. And the main difference to the the scattering compensation approach is that here we also have an active feedback loop inside the pipeline, meaning that we first predict all the effects of what our current solution is showing, and we can see the artifacts that we would see in a real 3D printout. And then in the second step, in the refinement step, we try to compensate and put countermeasures into place that reduce this lateral scattering and reduce the artifacts that we're seeing. And these are really the two building blocks that are different in the upcoming papers, and I will detail you these now. So I introduced you to these 4 papers before, but I want to give you a bit more intuition about them now. So first of all, in 2017, this paper was the first to introduce this active feedback loop into the printer pipeline. And they used a Monte Carlo renderer for the forward approach and developed a heuristic that is based essentially also on observations and intuition and how to counteract these effects. Later in 2019, we applied the same approach to 3D objects and also adjusted the heuristic to compensate for problems that we see on very thin geometry, as in, yeah, like the cat's ears, for example, there. And because the Monte Carlo rendering is not very practical, in fact, it's like computationally very, very expensive, we went on and developed a neural network to speed up this process, replace the renderer essentially in this loop, but kept the heuristic in place that would be, optimizing the 3D printouts. And then in the last paper, we scratched, like we took the knowledge of all this previous work, but we started from scratch with a completely new approach and used differentiable rendering for optimizing the 3D printouts together with a gradient descent optimizer. So there's no more heuristic in play, but actual gradient descent optimization. So so for the Monte Carlo forward prediction, so excuse me. So I want to now tell you a bit more about these building blocks in detail and how they work. So for the Monte Carlo forward prediction, we can essentially use an off-the-shelf volumetric renderer and then measure like if we know the material's properties, we can again get a rather accurate simulation of what's going on. And we also see all these artifacts that we see on the real 3D printouts happening in the simulation. And to facilitate that, in a normal path tracer, usually the appearance is a product of the surface attenuation. In this case, it's a dielectric plastic material. Then the subsurface scattering part and the illumination which shines on the object. And in a 3D printer, all you can control is essentially the subsurface scattering part, and with some post-processing, also the surface part. And so in our simulations, we scratched essentially the illumination part, factored it out, and put a 1 there that is then propagated through this formula to give us a simulation of what the subsurface scattering part is doing. And this makes sense because later on when we 3D print this object, then the reality will essentially be multiplying the illumination on top of our objects. So if we assume a 1 there, then it will just reproduce, it will just work with any illumination, so to say. This is very generalized. Don't nail me down on that. So once we have that forward prediction, we can compare this to what we actually wanted to print in the first place and get a sort of a difference image. So we get a positive and negative delta to what we want to achieve. And this difference map is essentially defined on the surface, how we want to change the surface appearance to get closer to our target. But now the challenge is, how do you distribute this error on the surface into the volume? Or in other words, how much do you need to change your volume such that you get a differential change on the surface? And the heuristic approach to this works in the following. So any negative residual there, which means is the surface is too bright and we want to darken it down, gets propagated from the outside to the inside. And similarly, any positive change means that the object is currently too dark and we want to brighten it up, is getting propagated from the inside to the outside. And the way this works is that colors are only, this arrow is only propagated once colors are saturated. So if it hits a 1 or a 0 in the voxel, then the remainder is getting propagated to the next layer. And the effect of this heuristic is that any absorptive material gets compressed to the surface. So here you can see that the surface is actually a black layer with highly absorbing material. And underneath is only a little bit of other materials, but not much. Essentially, most of the absorption gets pushed towards the surface because this minimizes any lateral scattering effects that would cause the blurring or the crosstalk. And intuitively, this makes sense. So the deeper you put any absorptive color material, the more distance it needs to travel back to the surface. And it means also that the wider influence it can have on more points on the surface next to each other. And in case of thin geometry, we modify this a bit and say, instead of only propagating towards the closest surface point, we also propagate the lightening part towards the other closer surfaces. And that means that both of these sides will be separated even further, and any of absorptive material will be pushed away from each other. So you separate these two sides better. And here I want to show you an animation where we see the surface prediction on the left side. And on the right side, I cut the object open and you see a visualization of what's inside the printer, like inside the object, the internal structure of the voxels. And in the background, I'm plotting an error plot where you can see that roughly about here, after the 7th iteration, the error reaches a minimum, and this is essentially where we could stop the optimization. But I let it run here to show you that it kind of reaches this minimum. I'll play it one more time. Okay, so now let's look at some results here. If we want to print these vases, then what we saw with the default printer software at the time, and also the cuttlefish version at the time, is that they show this kind of the blurring that I showed you earlier. And with our approach, you were able to get a significantly higher contrast and sharpness back of the texture. Like this very fine details become suddenly visible. Unfortunately, this method is not very practical. It's in fact, it's very far from practical. So we asked ourselves, how can we make this faster? And well, everybody did machine learning, so we tried, well, let's also do machine learning. Okay, so here's the two vases again, the same vase again, 2 times. One's optimized with the Monte Carlo simulation, on the right side with a neural network. Now, you will probably not notice any difference between the two pictures, and that is intended in fact. But what the difference is that instead of using a big CPU cluster for a long time, we can push the computation requirements quite a lot down. We can use a desktop computer with a GPU equipped and can run this in the order of 2 minutes per iteration. And this is quite a significant speed up. And the way this neural network works is that instead of shooting any rays, like we did in the Monte Carlo simulation, we are trying to predict the surface appearance for each surface voxel with the network. And we do this by picking one surface point. And then for this surface point, the black point in the center there, we want to predict the surface, the appearance. And we sample the materials that are around it in a certain grid and look up what the materials are around this point. Then for these, we look up the scattering and absorption coefficients, which we then feed to the neural network, and we get a single radiance value out of it. This radiance value we can then put back into our voxel grid at this position and be done. Now this loop essentially also repeats itself for all color channels or spectral channels, if you will. So this is color independent. It can be run as many times as you want. And during the training, we of course use many different objects with different geometries and different colors. But it's not very different from the inference time, where we just take surface points from a single object, run all of them through the network in a batched way, and then get the surface predicted out of this. Now, if we look at some results again here, I hope you again don't see a difference between the right two columns as it is intended. So we want to persist the high quality of the Monte Carlo simulation, but we wanted to push down the computational demand and the runtime quite significant. And I think we achieved this here by bringing the method into an order of minutes from the order of hours. So I've shown you now how to use one popular technique to solve this problem. Now, what about this other booming effect called differentiable rendering? And can we also use that? So what is differentiable rendering? This is a technique that also got popularized in the last few years. It's related to normal Monte Carlo rendering that you see here on the left with this nice dining table scene. And what differentiable rendering computes is essentially a first derivative of the image with respect to a scene parameter. In this case, the scene parameter is the location of the sun. So if I move the sun up and down, how do my pixels change in the image? And I don't want to go into any more details here. I want to refer you to the excellent tutorial by Zhao et al. That was published in last year's CVPR. And this is available freely under diff-render.org. So for us in 3D printing, the scene parameters that we are tweaking essentially the millions of voxels. And remember when I asked, when I showed you this picture and I asked, okay, how do we need to change the volume such that we get this change on the surface? Well, this is exactly what the differentiable renderer gives us. In fact, it computes the partial derivative of the surface with respect to each single voxel. And So you can pack this partial derivative into a gradient descent optimizer, such as Adam or Adagrad, whatever you want to use. You all know them from your machine learning work, and be done with it. Well, it's not quite as easy. In fact, you need to make the whole pipeline differentiable for it to work, because this is a chain, and as soon as one link breaks, it doesn't work anymore. So in the paper, we show how to model a problem in a differentiable way, how to apply constraints, and especially in this case, you need to have a loss function which is working over a surface of 3D voxels, and you want to express certain properties in that, and this is all part of the paper. So in these results that I'm showing you here, we can essentially prove that the new method of differentiable rendering is giving us the same accuracy in terms of the scattering compensation as the previous method. But you notice that the colors here are a bit different, and that is because this new loss function actually has a weight for between color accuracy and sharpness. And there seems to be some sort of trade-off in the material space, that you can either go for more color accuracy, but lose a bit on the contrast, or you focus on the contrast and you lose a bit on the color accuracy. So there's some leeway there. So with that, I wanna show you. Okay, I showed you the Monte Carlo rendering as a forward model, as well as the neural network as a forward model, and the heuristic as a backwards step that is used for both of these methods. And I also showed you how to use the differentiable renderer and a normal gradient descent optimization in the appearance 3D printing space. And I hope I could both Philipp and I could convey you that color 3D printing is a very interesting field, and it's at the intersection of so many different fields, being fabrication, volumetric light transport. There's material science of physical properties. Optical measurements is a big part of it, which we didn't even talk about today. And there's a lot to be done still. And second point I want to make is that an active optimization loop is really the key to get control over the limitations that the printers are imposing on us in terms of appearance. And with that, I want to thank you for the attention, and I want to thank my collaborators for all the good work that we've been doing together. Thank you.
Thank you very much for the talk, and we have some time for a couple of questions. So first question is for Philipp. When you were mentioning the general trend of appearance reproduction, that in the future we could see more joint appearance of both translucency, gloss, and color, you kind of hinted at the challenges which are associated with such reproduction at the start of your talk, when you're mentioning that these are rather high dimensional spaces. There were 3 for color, 5 or so for gloss, and 4, I believe, for translucency. The question is, are these independent dimensions, or do these crosstalk between each other? Is gloss also affected by the color and vice versa?
Yeah, actually, that's an excellent question. Actually, there are some crosstalk. So there's some for example, if you have there are some psychophysical experiments done in the past where you have, for example, a glossy object with some specular highlights, and then you remove the specular highlights, and the color changed. The color that were judged by observers changed. So this is, I think, one of the biggest challenges to find a model of visual appearance that can be used to optimize the reproduction. And this model needs to consider all these interactions between attributes.
And can this be considered purely in terms of the appearance descriptor, or do we also need to take into account what we are printing, the geometry, and perhaps even where we are looking at the material? Is it different to optimize for something outside, inside, based on the light sources?
Not sure if I understood the question, but if it was a question that the shape plays also a big role in the whole reproduction.
The second part was more associated with something like you have spectral chorus, which then if you manage to get a spectral reproduction to look the same regardless of the illumination, is there something like spectral translucency and spectral gloss?
Oh, okay. Yeah, sure. I mean, you have different absorption and scattering coefficients per wavelengths, which means there are materials that also scatter in different wavelengths differently. However, what needs to be investigated, and I think nobody has done this so far, is to check what the human visual system is really capable of detect and what kind of tolerances are acceptable. So we have seen that for the translucency reproduction, you can accept a big error in terms of physics. No, in terms of perception. So the physics create a big error, but the perception is still quite small. So if you have, for example, we have reproduced human skin that look pretty natural, but if you measure the absorption scattering, they are very different, because the human visual system just looks at different cues that what I mentioned in my talk, and these cues are not changed as drastically and to really downgrade the quality and the match.
I see. So now a question for Tobias. You were mentioning that you cannot use completely opaque materials because you want certain amount of translucency, for example, to also print in translucent. But at the same time, if you would have more opaque materials, then the rate at which you could affect the geometrical properties would be significantly lower. You would not have this discrepancy of 10 centimeter scattering versus these tiny voxels. So is there a sweet spot as a trade-off between these two, or would it pay off to have two different materials, one more translucent and one less translucent in the printing system?
I think this is the way to go. Like if you want to print translucency, right? Obviously, you need translucent materials. You cannot print translucency with opaque materials only. That doesn't work. So, yeah, in my opinion, what we will see in the future is that we will get banks of tens and 20s of printing materials, and then we can just print with all of them at the same time and mix them together. In some further future, I would say. So yeah, of course you can reduce this this translucency by an order of magnitude, by 2 orders of magnitude, but there's still some will still be there, and you will only try to minimize this effect.
Then I have a question for Philipp, and it is maybe a bit of a tangential question. It is about the new printing heads that you were mentioning, that they would enable translation from prototyping parts to production parts. And the main benefit is the durability. And is the durability also improved along the printing direction with these new heads and materials, if you know the answer to this question? Or because currently part of the problem with printing is that you have more durability along and less perpendicular.
I mean, the printhead is just a way to jet material. And in order to answer this question, you need, of course, to know the whole system. You need to know how strong the UV lamps are. You need to know how the material is actually deposited. Usually, we have this kind of idealistic view on this voxel printing, that the voxels are just cubes, right, next to each other, but in fact, the droplets are mixed. And what is also not the case is that the voxels are just stacked on top of each other. If you go into the Z direction, they are typically interlaced in order to improve the structural integrity of the object. So one voxel is here, and the next voxel is somehow 50% in that direction, 50% offsetted. Right? Mm-hmm. So, and this is something that that already improves the structural integrity in different dimensions. And I think using the high viscosity materials will just improve everything in all directions. But I can assume that there would still be an anisotropic anisotropic
instability or breaking point, or
a breaking point. Yeah. So you basically break. I guess in Z it will always be lower than in X and Y, because the materials are already cured, right, or partly cured, and then the next layer will come. Right. So in X and Y, this is not the case. Material are mixing
before they cure.
I think in SLA materials, they or SLA printers, they actually try to minimize the pre-curing as much as possible, and then rely on the light again going through even quite a few layers backwards to then have the multiple layers better stacked together and cure them together essentially while they already printed, not pre-cure the whole layer, then print the next one on top of it. Yeah.
I mean, in maybe one more thing is you have also this leveling mechanism in polyjetting. So there's a small a blade or a roller that just makes sure that after printing 10,000 layers on top of each other, and you have always like 5% of
you're not printing this way.
And everything is completely messed up in that. So this definitely also impacts the whole stability in that.
Because that physically cuts the material every time, right?
It cuts and pushes materials into holes. Typically, a little bit more is printed, and then the leveling mechanism is a roller that pushes the material downwards, the pre-cured material downward. But then everything is pretty flat. And printing on something which is flat is definitely not as stable as if you would have some bumps. And then
there's no adhesion anymore. Yeah.
I see. So then a question for Tobias. You have mentioned replacing the traditional rendering via a machine learning approach. And the question is if this method is only suitable for optimizing the color of prints, or could it also be used to accelerate rendering in general?
It is surprisingly generalized, actually. So it's although it was trained on 3D printouts, it could be used in a general renderer to predict a heterogeneous volume scattering, with one exception, and that is that the training data assumed this constant illumination over the surface. So you will not have like lighting effects that are directionally or affected. You only have a diffuse illumination for this object. But if this is happening in your case, then you could also use it for a general purpose renderer. But this method is actually based on prior work in rendering, which was developed as a general purpose renderer for directional illumination. So I guess that could be used in that case as well.
And the last question is for both speakers. And that is that at the core, the methods presented today are optimizing the placement of materials to get some desired functional characteristic. In this case, it was the look. But do you think these approaches could generalize to getting, for example, the desired material behavior or when we have the new printing heads with even more interesting materials, since we can now load them with particles, perhaps getting some more functional behavior, perhaps even in terms of printed electronics or similar cases.
Maybe I can answer first. I think some of the methods can be definitely used. For example, if we talk about a half-toning method, a blue noise half-toning will definitely be also optimal for material gradients when it comes to mechanical stability or mechanical properties. Some of the methods, of course, are just optimizing visual appearance. I think when I understood it correctly, the light transport approach is relatively focused on the how light goes through the object. So I don't know if you can generalize this to other properties, maybe mechanical properties. I have a doubt, but I don't know. The standard pipeline is here. It's possible you can reuse, and this is something that we did already. A lot of these building blocks, and just get rid of the perceptual block, perceptual optimization block, and use lookup tables that optimize material properties, for example. And this is also done in industry a lot already.
Yes. So Philip, you're right. Like a pure renderer will not optimize a mechanical properties of a 3D printer. However, with this in this differentiable framework, you can plug in anything that is differentiable. So that goes from machine learning networks to differentiable physics simulations, which already pop up at SIGGRAPH for quite some years now. So I could believe that you could plug this together and make this happen. And in fact, I recently saw on your former colleagues, Michal, at MIT already have a system in place where they optimize mechanical properties. So they mix new materials, print them on the go, and test them in sort of an optimization loop. I think that already exists and is published. So yeah, it's a matter of years, you know.
So I would like to thank the speakers for their awesome talks and also for staying for the Q&A session. And now we will have a bit of an unrecorded chat that you could join through the Zoom link. So